So previously we have seen that size 2 stopping sets are very harmful and they lead to a pretty high error rate after decoding, which prevents us from using LPC codes on the binary erasure channel if we want to achieve very low error rates. Now in this video we're going to see how to prevent this from happening. So to summarize, the error rate performance that we have seen was rather disappointing. Now we ask ourselves the question, is there a way to fix the code and the construction to have better correction properties? So the idea is, if size 2 stopping sets are so harmful, why don't we do everything in our possibilities to avoid those? So we want to avoid size 2 stopping sets that will lead to better error correction properties. So let's take a look at the size 2 stopping set again. So here we have a size 2 stopping set, and we see that the size 2 stopping set contains something that is called a cycle. We have a cycle of length 4. So this is one cycle of length 4. We have more than that cycle. So we have another cycle that is shown here. It's another cycle of length 4. So we have cycles of length 4 in the graph. So what we can do is we can avoid cycles of length 4, and that will lead to a code that does not have size 2 stopping sets. That is what is called expurgating the graph, removing cycles of length 4. How can we do this? And why is this helpful? So there is a very nice result that is given here. So if we have a regular DVDC LDPC code and we have a tenor graph of girth G. So recall, the girth is the length of the shortest cycle in the tenor graph. So now we have multiple cases. If dv is equal to 2, the smallest stopping set has a size of G divided by 2. So if the girth is equal to 4, the smallest stopping set has size 2. If the girth is equal to 6, the smallest stopping set has size 3. By increasing the girth, we can increase the size of the smallest stopping set. Now for dv larger than 2 and girth being equal to 6, the smallest stopping set has size dv plus 1. And for dv larger than 2 and girth 8, the smallest stopping set has size 2 times dv. For larger girths, the situation is not so easy anymore, but these two cases are pretty easy. So increasing the girth to G equals 6 by eliminating the 4 cycles will lead to avoiding stopping sets of size 2, because then the smallest stopping set has size dv plus 1. So we cannot have a stopping set of size 2 anymore. And then we can approximate the error probabilities when all the 4 cycles are eliminated. So here is the result. We cannot give a good bound anymore. The calculation is pretty bad, but we can give an error probability. So if we have a regular DVDC LDPC code with no parallel edges and no 4 cycles, so the girth is equal to 6, then the errors are due to dv plus 1 stopping sets, and we can calculate the error probability of those. So again, the error probability is given by epsilon to the power dv plus 1. That's now dv plus 1 variable nodes must be erased. Much better, because this is going to be a very small number. Times n choose dv plus 1. So again, we need to find all combinations of dv plus 1 variable nodes. And then this is an approximation of the possibility that they form a stopping set. So we have already calculated enough. So we omitted the proof. If you like it, you can look at our own paper here where we show how this approximation can be done. So how can we identify and eliminate those 4 cycles? And that turns out to be actually pretty easy. So a fourth cycle is given by some very specific structure in the parity-check matrix. That's a so-called row-column condition. If two rows or two columns of the parity-check matrix have more than one position where they correspond to each other, we have a fourth cycle. So for instance, here we have these two columns. They have two ones in row 1 and row 4. So this actually forms a fourth cycle. And we can group those together. We see if we plot the graph, this will be a fourth cycle. So from this variable node to this check node, then we go to this variable node, this variable node going back to this check node, and so on. So this is an example of a fourth cycle. And what we can do now is we can avoid these by checking the row that this row column condition is not fulfilled. And this is the row column constraint. So what we can do is we can, for instance, take this one and swap it with another one. For instance, we could put this one over here. We can put this one over here. Then we don't have an overlapping one anymore. Then we have the situation that we have a 0 over here. We have 0 over here. 1 over here. And we're going to put the 0 over there, 1 over there. So we can just swap those. And we have avoided the fourth cycle. That's the so-called row-column constraint. So the row-column constraint means no two rows or columns of H must have more than one position where they both have non-zero components. And checking for this row-column constraint is very simple, especially if you have a computer algebra software like MATLAB. So if you have the parity-check matrix H, and H lowercase hi is the ith column of H. So this is column number 1, column number 2, up to column number n. So then if we calculate the dot product hi transpose times hj, and the operation is done over the real numbers, this is important. It's done over the real numbers and not over the field of f2. That gives us the number of overlapping ones in hi and hj. So we just calculate the dot product of all the combinations of hi and hj. That will give us the number of overlapping ones. So what we can do is we can, for instance, if we have MATLAB, we can calculate h transpose times h. That will do this dot product, and then we have also calculated hi transpose times hi, which will just be equal to dv. We need to subtract this. So this is being corrected here. So we take h transpose times h minus this guy, which removes the column I with column I. And then we have this matrix T, which for all the combinations of A and J contains a number of overlapping ones. We search for the entries that are larger than 1, and then we know that these two columns have more than one overlapping one, and then we can start removing. We just need to look at the upper trigonal matrix because I and J and I, they correspond to each other, so we just need to search part of this matrix. And then we search for the spaces where this is larger or equal than 1. Then we get the first and the second variable nodes where this is the case. Then we can just go through them and swap some of the entries in the code. Then we'll avoid the 4 cycles. So we have on GitHub, we have a program that's called remove 4 cycles, where we can remove the 4 cycles. And now what we do is we repeat the experiment from before. We generate a code, the 3.6 LDPC code, and repeat the code, but remove the 4 cycles afterwards. And that will lead to a smallest stopping set of size 4. So let's take a look at the result. This is what we get. So this is the result that we had before without any expurgating. And now removing the stopping set of size 2. By increasing the Gauss to 6, we lead to a significantly better error rate performance. So here we show also the bound, the lower bound, and the approximation for Gauss of 6. See that both are actually pretty good. The approximation is a little bit overestimating the performance, but that's not too bad. If you look at the reference that I showed there, we have upper and lower bounds. I just gave the upper bound because it's easier to evaluate than the lower bound. So you can also get a smaller value of this. So that's actually quite a big improvement of 2 orders of magnitude here in terms of error rate. That's actually quite nice. So if we compare this also for different lengths, so here we have the same graph as before. This is what we had previously, the curves for Gauss of 4. And now if we increase the Gauss to 6, then we plot the approximation and we see that we can push the error rates quite heavily down. Also now we are able to reach 10 to the power minus 7 with n equals 5,000. This is for 3.6 LDPC code. We go to 4.8 code, the situation will be even more severe. There we have the previous results down here, and now with n equals 5,000, we can get in the range of 10 to the power minus 15. So we can actually get pretty great error rate performance with n equals 15 and 4.8 LDPC code. Okay, so this is actually a pretty nice result, and this is actually what is being done in practice. So to summarize, so what we have found is stopping sets on the binary erasure channel prevent the decoder to reach low error rates. So we need either large N or large dV to push down the error rate sufficiently, but the large dV will lead to a worse threshold. Now we can get a significant performance improvement by expurgating the code, so removing 4 cycles. Removing 6 cycles will be even better, but that's not going to be easy. But that's something that's being done in practice also. So removing 6 cycles, removing 8 cycles, and so on. So this is for the binary erasure channel. Again, situation on other channels is not so easy. For instance, on the binary input AWGN channel, the stopping sets don't play a big role. There is something called absorbing sets that play a more important role. They are similar to stopping sets, but defined slightly differently to take into account the behavior of the message passing decoder on the more general channels. So now the analysis of absorbing sets is beyond the scope of this lecture, but it's essentially very similar to the LDPC, to the binary erasure channel case, slightly different. The main conclusion is that if we eliminate 4 cycles, this will tremendously improve the error rate performance of LDPC codes. That's the main takeaway. So removing and eliminating 4 cycles will tremendously improve the error performance of LDPC codes. So essentially, if you look now closely, now you have essentially all the tools at your disposal to generate a code for the challenge. You have the code for optimizing the degree distributions. You have the code for generating parity-check matrix. You have the code for eliminating the 4 cycles. So now would be a very good way to sit down and try generating a code and see what kind of code you can get for the challenge, for the parameters of the challenge. So with this, we stop this chapter. We are done for this week, and I'm very happy to see you again next week.